Hello all of you. Welcome to the 53rd lecture of the course on analysis and modeling in chemical engineering. In this week, we have been discussing about separation processes and how we can model that, particularly the equilibrium based methods for computational solution of separation problems, particularly cascades. In the previous lecture, we have discussed how we can use this BP method, the bubble point method, by guessing the temperatures and pressure, and that's what we said, a tiering approach for solving the mesh equations for a cascade in general. Today I will extend to some other methods which are used, which are somewhat more efficient compared to the BP method for solving the same kind of mesh equations, but we will modify the mesh equations as we will see in this lecture. So this is what we have been discussing for last couple of lectures. So we first took an equilibrium stage where we have a feed, it can be like a vapor or a liquid, containing an overall mole fraction Z, and this is the feed for entering the stage J, and some enthalpy and some temperature and pressure. And there is a counter current flow of a vapor and liquid. The vapor is going up, the liquid is coming down. So what enters stage J is the vapor from the stage below, that is the J plus 1th stage, which has some volumetric flow rate or molar flow rate Vj plus 1, some mole fraction Yij plus 1, some enthalpy and some temperature and pressure. And what I also enters is liquid from the stage above it, that is J minus 1th stage, with a molar flow rate of Lj minus 1, and again some mole fraction of different components, the enthalpy, the temperature and pressure. And what leaves from the stage J is the liquid stream going down, again with a molar flow rate of Lj. Along with that, we also have a side stream that is purged from the liquid going down, and both of these streams are going to have some mole fraction xy ij of different components, the enthalpies and temperatures and pressure. And in a similar manner, there is a vapor stream and a vapor side stream going from the top, which is again having some mole fraction y and some enthalpy and some temperature and pressure. We are assuming that there is an equilibrium, so the temperature in the vapor is same as the temperature in the liquid phase. Same is true for the pressure and same is true for the chemical potential. But for the chemical potential, we wrote in terms of the fugacity coefficients, and we got a general equation of the form yi is equal to ki xi. And then we wrote it for a counter current cascade containing stage 1 to n, and we have discussed the bubble point method. Let us look at some other methods for solving this equation. Right? So there is this method called the sum rate method that is particularly used for the absorption and stripping. Keep in mind that the vapor liquid cascade can be there for a distillation problem where we are using a ESA heat to basically create a vapor phase, or it can also be used for absorption and stripping where we are using an MSA, which is a liquid for absorption and the vapor for stripping. And for absorption, we are basically separating a component from a vapor mixture with the liquid MSA. And for stripping, we are doing the opposite. We have a liquid mixture and we have a vapor MSA. Right? So this particular method is better suited for absorption and stripping problem. So what we are going to do here is, in the very beginning, we specify all the feed rates going to every stage and the composition of the feed coming to every stage. Also the feed condition, the temperature, the pressure and the enthalpies. We are going to also specify the pressures of the stages, the molar flow rates of the liquid side stream Uj and the vapor side stream Wj, the heat which is removed from the stage J, and this we are doing for all the stages, and finally the number of stages. These things we are taking as given, and then we begin our iterations and we use tier variables, temperature and the vapor molar flow rates. And what we do in the main loop is the following. So we already discussed in the last class that the m equations combined with the E equations, we use the E equations to eliminate the y from the m equations. So we use yi is equal to ki xi and put it in the m equation. And what we therefore get is general equation of the form a j minus 1 xi j minus 1 plus b j xij plus c j plus 1 xi j plus 1 is equal to 0. So we have got a tridiagonal system containing the coefficient matrix having the terms along the diagonal, the upper diagonal and the lower diagonal, and all the other terms in the matrix is 0. Then we have an unknown vector for the x values, and that is equal to, by the way, this is some dj, some constant values, right? So we can use the Thomas method that we have discussed for solving the tridiagonal system, and therefore once we have guessed the temperature and the volumetric, the molar flow rate of the vapor, we can in fact use this equation to basically put it in there. But to use that equation we need the ki values, and the ki has to come from thermodynamics, and for that we need to basically provide the temperatures, because temperature will be going in the property relations that is there, right? So if I have that ki, I can plug it in there, and then I can get the values for these coefficients. In general, the value for this coefficient matrix and the constant matrix for the given guess value of the temperature and the molar flow rates of vapor, right? So using that x value, now I am going to first compute the new values of the liquid flow rate and the vapor flow rate, and then we are going to do a normalization of x, because x values are coming in the iteration, they are not the final correct values. So we need to normalize it as we will show, and we also calculate the corresponding y values, and then we also normalize the corresponding y values. And now since we began with a guess of temperature, so we are going to compute the new value of temperature. The new value of Vj also we have computed earlier, and then we check for convergence. I am not getting into the criteria for convergence, but basically we can look at the error or the norm of the error in the temperature and the vapor molar flow rates, and based on that we can decide on whatever tolerance I have chosen, that whether I have converged or not, and if not, then we basically adjust the tier variables using the new variables that we have computed in the loop, and we keep on doing this loop until the method converges, right? In fact, we have been doing this since we did the evaporators. The Bezer-McCabe method is also based on the idea of the two temperatures taken as guess, and then we had a scheme to update the temperature in every iteration. In the BP method also we have followed a similar course, but the arithmetic is going to be different for the SR method. So what we are going to do first is, once we compute this x, we are going to not normalize it immediately. What we are going to do is the following. We are going to do a material balance from stage 1 to j, and as we have shown earlier, I can compute the liquid molar flow rates from there, right? So if I do a balance from 1 to j, so Lj stream is going out, that's why we have a Lj here, and that is equal to what is coming in. So all the feed rates F1 to Fj, that is sum over Fm, is coming in. Out of that, what is being taken out from there is my side streams for the liquid U1 to Uj, again a sum of Um from m equal to 1 to j. Keep in mind that U0 is equal to 0 here, and W1 is equal to 0 here, and Vn plus 1 is also equal to 0 here, right? And then in addition to these three, we also have a vapor that is coming in, that is from the stage below. So, we have a Vj plus 1 there, and a vapor that is leaving out the first stage, that is why we have a V1 there, right. So, we can compute this Ljk for the previous value of my Vj, and now we are going to use this sum rate equation. Since we have now evaluated the new values of x in my loop using the Thomas algorithm, these new values of x I can use to update my Lj value, right. So, keep in mind that I have not normalized it. If I would have normalized it, then the summation of mole fractions should be equal to 1, right. But since I have not normalized it, and keeping in mind that xij are not the final correct values, they are what I get from the Thomas method. So, they by definition is not normalized by default. So, therefore, this term is not going to be 1 unless this xij becomes the final correct values. In that case, Ljk plus 1 will anyway become Ljk. So, the Lj is going to converge only when this xij is basically normalized by default without a need for normalizing by dividing it by something, right. So, I got the new value of the Lj, and then I can do also a balance from stage j to stage n. And what you see here is what is leaving this stage j now is my Vj, and I want to find the value of Vj for the new iteration. So, it is Vj k plus 1. I began with Vj k, and that is again going to be a sum over the feed streams, but now it is from feed j to n, and so we are subtracting the liquid side stream now from j to n, but un we are assuming it to be 0, and the vapor side streams wj to wn, right. And what is also coming in here is my Lj minus 1 from the stage above, right. This liquid side stream uj minus 1 I am not considering here, they will be considered in the top balance, right. And what is also leaving is my Lnk from the last stage, right. So, this is what is entering in the liquid, this is what is leaving in the liquid, this is what is entering in the feed, this is what is leaving in the side stream, and this is what is leaving in the vapor side stream. So, U and W are for liquid and vapor side stream. So, we are doing in minus out, and that gives me the net amount of vapor that is leaving there, right. I can write it in another way. I can move this thing to this side, that becomes a total material balance for stage j to n, but since I want to compute the new value of Vjk plus 1, I have kept it on the other side. So, now we have got this new Lj and new Vj, that is Ljk plus 1 and Vjk plus 1. So, we go ahead, and now we go ahead and normalize it, right. So, the BP method we normalized it immediately, but now we are normalizing it now. So, by normalizing, what I mean is dividing by the sum of xij, and this is going to by default satisfy the summation equation. This, because once I do a summation here, then the two terms are going to cancel, the numerator and denominator, and therefore, the summation of the normalized xij is always going to 1 by default. And now, I use this old value of temperature, whatever I have available, to get this k, and I can then compute yij as kij xij. So, kij is using the old temperature, but the new composition, and the yij for the new iteration is related to kxij for the new iteration, and again we have to normalize yij, which we are doing in a similar manner. So, the next step is we have to compute this Tj. Where do we get Tj from? We have to get Tj from the energy balance equation. So, we write the energy balance for the stage j, and in fact for all the j values, and now for the new energy balance I have the new value of the enthalpies, right, because the composition has changed in the iteration, and therefore it will give me a new value of temperature, right. Just to remind you of the energy balance of stage J, it is something like this. We have Fj HFj that is coming in, plus Vj plus 1 HVj plus 1 that is also coming in, and then we have Lj minus 1 HLj minus 1 that is also coming in, minus Vj plus Wj HVj that is going out, minus Lj plus Uj HLj that is also going out, minus Qj that is going to be equal to 0, right. So, when I am solving this, I am now using the new value of the Vj which I have computed there, the new value of Lj. Other things are already known to us, let us say Wj, Uj, Fj, they are all given, right. I am using a new value of Vj plus 1, I am using a new value of Lj minus 1, and these enthalpies, all these enthalpies are going to be a function of the temperature, the pressure, and the composition of the corresponding phase. So, now since we have updated temperature, we are going to get new value of the temperature, the pressure is given, and the composition is also changing in the iteration. So, this also I am going to change. So, the P is given, but for T and composition I am going to use the new value that will give me a new value of H. And this is going to be some kind of a nonlinear equation, and in fact we are going to have a nonlinear equation therefore for every stage. So, this is the Hj, the energy balance for stage J. So, in general you are going to have the energy balance for all the stages which are going to be all nonlinear, and we have the Newton-Raphson method that is based on the idea that I solve this Fx equal to z is equal to 0, where f is now this function vector and x is now the variable which I am solving for, that is going to be my temperatures of the stages. In the Newton-Raphson method, we follow the scheme that my x k plus 1 is xk plus delta xk, where delta xk, as we have discussed when we are doing this numerical methods of solving equation, is given as something like Jacobian dot delta xk is equal to minus fk. And now for the given iteration, the Jacobian becomes a constant matrix, and this fk is also a constant vector. So, therefore, we can get the delta xk, and we can essentially keep on doing this iteration, right. So, we have a Thomas algorithm to compute the new values of x, and then I get the new value of the tier variables Vj and Tj, and then I do some normalization and I go back and do the same thing until it is not conversed, right, until the temperature values become constant and the vapor flow rates also become constant. So, in the there is one more method for solving the equation which is called the Newton-Raphson method, right. So, I am also using Newton-Raphson in the SR method, but this method itself is called the Newton-Raphson method because this is a more detailed application or more elaborate application of the Newton-Raphson for the entire scheme of things, right. In this particular method, what we do is we change our fundamental variables from the mole fractions to the liquid and vapor flow rates, molar flow rate, right, for the component wise, right. So, we define variables of this sort. Vij is my molar flow rate of component I in vapor leaving stage J, and I define this small Lij as the molar flow rate. This has to be L, molar flow rate of component I in liquid leaving stage J, right. And the way we do that, so we are essentially changing the variables y to v and variables x to L. And the way of doing that is the following. So, we begin with the summation of the mole fraction equation, in this case the y equations, and I multiply with Vj, right. So, if I multiply with Vj on both sides, the Vj comes inside the summation and Vj comes here in place of 1. And what is the Vj into Yij? Vj is the total vapor molar flow rate multiplied by the mole fraction of component I. So, this quantity is going to give me my Vij, that is the molar flow rate of component I in the vapor leaving the stage J. That is exactly what we did here. Same thing we can do for Sx, same thing we can do for Sx, and we are going to get the liquid molar flow rate Lj as sum over the liquid molar component flow rates, right. Okay. So, once we do that, then our earlier M equations, the material balance equations, which was in the terms of the mole fraction of species in the liquid and vapor, now I rewrite that equation in terms of the component molar flow rates in the liquid and vapor. So, I am going to replace x with L and y with v, right. And we defined some other variables to simplify our arithmetic. So, we define a variable Sj, which is the ratio of the liquid side stream to the liquid main stream. Capital Sj is the ratio of the vapor side stream, the molar flow rates of that divided by the molar flow rates of the vapor main stream. And I also define the molar flow rate of component J in the feed stream, that is the total feed molar flow rate multiplied by the overall mole fraction of component I in the feed, right. So, if I do that, let us say the first term, let me show you, the first term is going to be something like this. I can now take Lj common. I have defined small sj as uj by Lj. So, I can write Lj plus uj as Lj into 1 plus Sj, and now I have Xij, and Xij into Lj is my small Lij. So, therefore, this becomes Lij into 1 plus Sj. Similarly, the second term is going to be Vij into 1 plus capital Sj, and here we are multiplying the total liquid molar flow rate by the mole fraction of component I. So, this becomes small l, and similarly this also becomes small v, and this by definition of this small f becomes small Fij. So, once we have done that, then we also go ahead and rewrite our E equations, which was also originally in terms of the mole fractions of component I, but now I want to express in terms of the molar flow rate of component I. So, I am going to replace Yij essentially by Vij by total molar flow rate of vapor Vj, but this Vj has to be the sum over the component molar flow rate in the vapor phase, right. So, this is a sum from 1 to C of the component molar flow rate Vkj. Keep in mind that I have introduced dummy variable k here because I and j are the running variables here. So, here I am doing a summation over the component molar flow rates to get essentially my Vj. So therefore, I have introduced a dummy variable, not to confuse with the variables I and j, right. Similarly, I can replace xij with this quantity, and now I will have, after some rearrangement, so this quantity will go on the other side and I multiply by -1. So I am getting some expression like this, which is my revised expression of the E equations. I also go ahead and rewrite the H equations, the energy balance equation. So by whatever logic that we have given, this becomes Lj into 1 plus Sj into HLj, right, and Lj again I can replace with the summation over all the components of the component molar flow rates, small Lij. So therefore, this gives me the first term appearing here. Similarly, we have for the vapor, we have Vj into 1 plus capital Sj Hvj, and this Vj can be written as this summation. So the second term gives me the second term here. Now similarly, for the third term, Lj minus 1, I can write as summation over I1 to C Li for j minus 1. That gives me the third term here. Similarly, we have the fourth term. All the liquid and vapor total flow rate I am replacing by the summation over the component molar flow rate, because that is my new variable which I want to work with. Similarly, Fj, the feed molar flow rate, is the sum over the component molar flow rate in the feed, and Qj is as it is, right. So now we have this final set of equations. I already have used the S equations in my very first step to basically rewrite the equation in terms of the vapor and liquid flow rates. And since I have eliminated the Vj and Lj in the equation, I don't worry about these equations anymore, because the variables Vj and capital Vj and small Lj, wherever it was appearing, I have replaced by this summation, right. So the final equation, we have an MEH equation in terms of only the liquid and vapor component molar flow rates, right. And then we can basically see that we have an Mij equation, the M equation for every component in every stage. So in total we have NC equations. I rewritten the E equation. Again we have N stages, C components, total NC equations, and then we have N equations of energy balance, one for every stage. So total we have N into 2C plus 1 equations. So we can define N into 2C plus 1 unknown variables, and let us choose the unknown variables as component molar flow rate in the liquid stream and the component molar flow rate in the vapor stream. So again, these are defined for all the components in all the stages. So we have NC variables, and this is also NC variables, and the temperature of every stage, which is going to be N variables, one for every stage. So this is going to be my solution scheme, whatever I have discussed earlier in the SR method, but keep in mind that now it is applied on the entire set of equations, right. In the sum rate method, the x was coming from the Thomas method, and then I was having some other relation for the SR relation. I was normalizing, and I was only computing the Tj using Newton-Raphson method. So only the H equation were being solved by the NR method, right. But in this method, which is called Newton-Raphson method, we are going to solve this entire set of MEH equations by the Newton-Raphson method, right. So we are going to define a function vector, right, and an unknown vector. These are my N vapor component molar flow rates, the temperature, and this particular order is also important for what we will see, and the component liquid molar flow rates, and we now get essentially a function vector here, and I get similarly the function vector in terms of the equations, right. So, I first write the equation for energy balance, and then I write the m equations, and then I write the E equations, then I write the E equations, right. So, we have one equation here, an equation here, an equation here. So, we have total, sorry, C equations here, C equations here, total 2C plus 1 equations, and we have 2C plus 1 variables. But this 2C plus 1 equation and 2C plus 1 variables are for a given stage j, right. So, one of the x that you see here, that essentially is a vector, right. So, in reality what you have, so you have, sorry, this also has to C, right. So, we have 2C plus 1 variables and 2C plus 1 equation for every stage. In total we have n times these equations and n times these variables for every stage, right. So, my x vector is going to have total n into 2C plus 1 variables, but they are going to be in n blocks. So, we will have one block for the first stage containing these 2C plus 1 variables, then we have another block of the stage 2 variables, then another block for stage 3 variables, and so on, right. So, let me write it for first two stages. So, I will have something like V11, V21 until Vc1, T1, L11, L21, LC1 for the first stage. That becomes my first block, and then I am going to follow this up with the same thing for the second stage. Right, and I keep on doing it for all the n stages, right. So, we have n blocks containing 2C plus 1 variables, and total we have n into 2C plus 1 variables, but they are appearing in this n blocks, right. The same is true for functions. This 2C plus 1 equation is for stage j, right. So, for every stage I am going to have a block in that function containing these equations in this particular order. The order is also very important here, right. So, for example, we will going to have something like for first stage H11, M11 until MC1, and then E11, E21 until EC1, and this we will follow with this the second stage H2, M12 until MC2, E12 until EC2, right, and I keep on doing it for all the stages, right. And then we will apply the Newton-Raphson on this entire thing, right, and we are going to see that the same kind of a scheme, that I will use this kind of a Jacobian. What we see is that now we form not a block tridiagonal, not a tridiagonal matrix, but a block tridiagonal matrix, which we have discussed long back, right. So, now the terms that you see here, these are not really scalar quantities. These terms are basically matrices. These terms are all matrices containing 2C plus 1 into 2C plus 1. I can call it a submatrix as the components, right. So, each of, let us say you see B1, C1, all of them are submatrices, we can say, having 2c plus 1 into 2c plus 1 elements, right? And this zeros you see, they are also basically matrices of the same dimensions, 2c plus 1 into 2c plus 1, but containing all zeros. So, what we see here is now a block tridiagonal matrix as opposed to a tridiagonal matrix, which again we can solve using Thomas algorithm, and we have discussed this when we did the numerical methods of solving equations, how we can extend the Thomas algorithm for tridiagonal matrix to a block tridiagonal matrices. And just to demonstrate how this matrix looks like, it is somewhat, I would say, a sparse matrix. It contains very few terms, which is non-zero. For example, this AJ, that is my lower diagonal, is going to look like something like this. The Jacobian is going to look like this. So, all the empty space you see here, they are all zeros. Where you see this plus, these are having some entries, plus or dot dot dot, they mean the entries. And wherever the entry has a fixed value, let us say -1, I am putting the value there. And every other thing that you see here, that is empty space, they are all zeros. So, this is an example of a 2c plus 1 into 2c plus 1 submatrix, I can say, for the quantity AJ, that is the lower diagonal, right? And what does this correspond to? It is a Jacobian. So, Jacobian basically correspond to derivative of the function with respect to the x variables, right. So, we have the function vector for the jth stage, and I am taking a derivative with respect to x. In fact, we are doing it term by term. So, for example, this is going to be something like dou hj by dou v1 j minus 1, and the next term is going to be something like dou hj by dou v2 j minus 1, and I keep on doing it, right. Let us say here we are going to have dou ecj by dou v1 j minus 1, and we keep on doing it. The last term, for example, is going to be dou ecj by dou lc j minus 1, right. So, the variables are listed along the columns, and we are taking derivative with respect to those variables, and the functions are listed along the rows, and we are taking derivatives of those functions along the rows with respect to the corresponding variables in the columns, right. So, in reality it is going to be quite involved task, but therefore, we need computers for solving it, but that is the fundamental scheme that gets in there, right. Similarly, we are going to have the B matrix, that is the diagonal terms in my block tridiagonal matrix. It will look something like this. Again, this plus thing tells me things which are non-zero, right. All these terms are going to be essentially non-zero, but everywhere else you see an empty space, you are going to have basically all zeros, right. So, this column, this what you see here, these are going to have elements, but other things are going to be 0, right. Same is true for the upper diagonal Cj, and now it is a derivative for the j plus 1, that is the stage above, right. And we can populate matrices which are containing still plenty of zeros. There is all sparse matrices, but nonetheless it provides a kind of a framework that we follow, right. Okay. So, what exactly we are doing in all these methods we have discussed, whether it is a BP method or a SR method or the NR method, there is one part of the story that I have not discussed in detail of how exactly we are computing Ki. They are coming naturally from the thermodynamic models, but I am not mentioning which models are there, right. You can imagine that the models are going to be complex, right. The simplistic models, let us say the ideal gas model, is not going to explain what we are looking at. It is not applicable to liquids in the first place, right. I can apply a slightly less approximate model, let us say the ideal solution model, but then also we are going to have problems, if not explain all the non-idealities. So, in reality, we are going to have rather complicated models or things which are coming from correlations of, let's say, the gamma and the fugacities phi and so on, right. Of course, there are recommendations in softwares of what models to choose, and they have quite detailed mathematical models out there, right. But what I want to highlight here is that in every step, implicitly, we are solving those complex thermodynamic models, right. Let us say, for example, in the SR method, we are solving this. In the SR method, we are solving this H equations using Newton-Raphson method, and all these small h values you see there, they are coming from the thermodynamic models, and wherever I am expressing y in terms of x, there again I am using thermodynamic models, and if they are having a complicated form, it is going to be numerically quite intensive to do compute the thermodynamic models in every step of the iteration, right. And that is the main computational cost of these iterative schemes, whatever we have discussed, whether it is a BP method or SR method or NR method. What is kind of hidden inside the arithmetic that I have done is the fact that there is a complex thermodynamic models which has to be solved in every iteration, right. And of course, I have a choice of using a simpler thermodynamic model, but it is not going to give me an accurate representation of the system that we are having, right. And these are my guess variables which are getting updated, right, or the variables that gets updated in every iteration, right. There is an alternate way of doing it that will reduce computational cost and can provide faster, more efficient simulation software, and that is the following. What we do is some part of the iteration we perform using approximate thermodynamic models, and the other part we perform using complex thermodynamic models, right. As an example I am showing here. So, you have the mesh equation that has to be solved, and let us say I define some quantity here Sij, that is a stripping factor, by the way, that has to be recomputed in every iteration. That recomputation I am doing using an approximate thermodynamic model. But then once that iteration is over, then I have an outer loop, where I involve the complex thermodynamic models, right. So, only some inside iterations that I am using in my computational code, some inside iterations are being done by the approximate model. So, there is going to be fast, but I am not compromising accuracy, because there is also an outer loop that is using the complex thermodynamic model. So, the final results are going to satisfy the complex thermodynamic models as well, right. This is what is done in the inside out method. So, I will not have time to discuss all the details that go there, but I hope you get the fundamental idea that since we are solving thermodynamic models in every iteration, can we, for example, divide this into two loops, an inner loop and outer loop, and use approximate models for the inner loop and then a complex model for the outer loop and so on, right. We can of course read more details in books and software manuals that you are using. Okay, so with that I kind of conclude the discussion on the different equation tiering methods for the equilibrium simulations, and there are some applications where these methods are particularly recommended. For example, the BP method is particularly good for distillation problems involving narrow boiling feed mixtures, where the boiling points of components are not too different. If they are very different, then the BP method is going to have slow convergence or no convergence or instabilities and so on, right. So, if we are in a narrow boiling feed mixture and we are doing distillation problems, keep in mind that whatever vapor liquid cascade that we have done, it is as applicable for distillation as applicable for absorption and stripping process, because in both the cases we have a vapor liquid equilibrium, right? But then some method is particularly suited for some class of problems, right? Many of this comes from experience, but some of them also have a reason based on the actual math that gets in the methods, right? The SR method is particularly suited for absorption or stripping problems, and it can handle quite wide boiling feed mixture. So the BP, the boiling point, can be substantially different. And there is a way to extend this method for the liquid-liquid extraction, which is called the isothermal sum rates method. I have not discussed it, but it is quite similar to the SR method that we have discussed. Then there is a Newton-Raphson method. Since we are solving all equations together by the Newton-Raphson scheme, this method is quite versatile. It can pretty much hold for any type of column configuration, for any kind of feed mixture. It happens to have a better convergence than the inside out method, but also sometimes slower than compared to the inside out method. And there are ways to further improve the convergence by doing some kind of a relaxation. We have discussed the idea of relaxation long back when we discussed the direct and partial substitution, right? This kind of an idea can also be incorporated inside the NR method. So when we are doing xk plus 1 as xk plus delta xk, and I am computing delta xk by something like jk into delta xk as minus fk, I can also, for example, introduce a parameter alpha here that will slowly relax it rather than whatever is given by the Newton-Raphson scheme, right? But of course, there are more details which I am not getting into. So in some cases, we can go for a slower version of that method, that is a relaxed version of the method, in order to further improve convergence than it is required. The inside out method, for the reasons that I just discussed, that it is using this approximate models for the inner loop, it is going to be computationally efficient compared to NR in general. But then if the liquid mixtures are quite non-ideal, in that case it may fail to converge, right? But it is as versatile as NR. It can pretty much hold for any kind of column configuration, for any kind of phase mixture. So with that, I conclude this lecture. Thank you.